Okay, we're on 4.3, the solubility product constant. We're going to do the warm-up. Let's define solubility. This is the maximum amount of solute that can dissolve in a given volume at a certain temperature. Okay. Let's shift to math for a second. How would you define product?
Like two numbers.
Two numbers multiplied together? How would you define constant? Something, a number that stays the same. Okay, so the reason we're talking about solubility and product and constant is because you're going to soon see that when a salt dissociates, you can take the concentrations of the ions and multiply them together, and you'll get some constant called the solubility product constant. So I'm going to teach you how to do that. First, let's take a look at question 2. We need to practice just some basic unit canceling before I get into it. It says the solubility of lead 2 chloride is 4.4 grams per liter at a certain temperature. Write the balanced dissociation equation for lead 2 chloride. What's the chemical formula for lead 2 chloride? PbCl2. Okay, so if I have PbCl2 and it's dissociating, what ions am I going to form?
Pb plus 2. Cl minus 1.
And
2Cl.
2Cl minus 1s. Okay. If I asked you to calculate the molar solubility of lead 2 chloride at this temperature, I need to use this solubility and convert grams to liters to moles per liters. So we're going to take 4.4 grams of lead 2 chloride per liter. And if I'm trying to get molar solubility, which is moles per liter, which unit do I need to convert? Grams. So we're going to convert grams to moles. And the molar mass of PbCl2 is 278.27. So grams will cancel. I multiply 4.4 times 1 divided by 278.27. You're going to get 0.016. Easy enough? Okay. If I wanted you to calculate the concentration of lead 2 and chloride ions in the solution using this molar solubility, could you do that? Yes. So if I have one lead 2 ion, then wouldn't it be the same concentration? So the concentration of lead 2 ions is 0.016. And then the concentration of chloride ions would be what?
0.032.
0.032. How'd you get that?
And multiplied by 2.
Multiplied by 2 because we have 2 of them. So 2 times 0.016 is going to be 0.032 molarity. Yes? This is literally what we're doing through the whole section. Okay? So let's talk about equilibrium of saturated solutions. If I have a saturated solution of lead 2 chloride, that means I have some undissolved solid present, and I also have lead 2 ions and 2 chloride ions. So notice that when we're at equilibrium with a saturated solution, I have a solid on the reactant side. I have double arrows. and I have my ions on the product side. So the rate of the forward reaction where I'm dissolving this solid to create the ions is going to be the same as the rate of the reverse reaction where these ions are coming together and recrystallizing. Okay? So you know that I can write a KEQ expression from this. Agreed? And you know that I can't include a solid in that KEQ expression. And you know that if I have a coefficient, it becomes a exponent, right? So since we're dealing with a special type of equilibrium, it is in solution, it's a saturated solution, we're going to call this the solubility product constant. So this little EQ right here is going to become an SP. So everything else is the same based upon what you've learned in the past. It's just that this is a special type, okay? Okay, so let's take a look at the next page. And just to make sure you understand, solubility and solubility product constant are not the same. Solubility is the amount of substance or the maximum amount of a substance that you can dissolve in a volume of solution. Solubility product constant comes from multiplying the concentrations of the ions together raised to the power of their coefficients. So that's outlined for you here in this shaded region, okay? If the temperature increases of a solution, can't I dissolve more salt in it, generally speaking? So as temperature increases, I'm going to have more ions in solution, so when I multiply those ions together, my solubility product constant will also increase, okay? So let's take a look at the quick check here. Write an equation to represent the equilibrium present in saturated solutions of the following. So we've got strontium carbonate. What's the chemical formula for strontium carbonate?
SrCO3.
SrCO3. And since we are at equilibrium and it's a saturated solution, you're going to have a solid. On the reactant side, you have to include double arrows. You'll have your ions on the product side in the solution, and it looks just like this. Easy enough? Okay. Should we do one more? What's the chemical formula for magnesium hydroxide? Two. Okay, this is a solid. I have my double arrows. What ions will I form?
Mg plus 2 plus 2OH minus 1.
Good job. Easy enough? Everybody can do this, right? Okay, we want to write the Ksp expressions for A and B. So here, this would be the concentration of strontium ions times the concentration of carbonate ions. And we will not include this solid, right? This is omitted. Solids and liquids are omitted. Here, the Ksp would be the magnesium ion concentration times the OH minus concentration raised to the second power because you had a coefficient of 2 there. And the coefficients become exponents, and we would exclude this solid. Okay. Now, I'm going to teach you how to calculate the Ksp from the concentrations of ions. So we're going to skip forward to practice problems on calculating Ksp from solubility. Okay. It says calculate the Ksp for each of the following. CaCO3 has a solubility of 6.1 times 10 to the negative 5th molarity. So I'm going to write CaCO3 with my calcium ions and my carbonate ions. And if they tell me what the solubility is and it has a unit of molarity, then I can use that to determine the concentration of my ions in solution. So this would be 6.1 times 10 to the negative 5th because I have one of them. And the same would follow for my carbonate, 6.1 times 10 to the negative 5th. Okay, because when we're at equilibrium and it's a saturated solution, I've dissolved the maximum amount of ions that I possibly could. So if this is the solubility of calcium carbonate, this is the maximum amount of ions I could have for each. Okay, so the Ksp expression would be the calcium ion concentration times the carbonate ion concentration. I omit the solid. I substitute these concentrations in, so this is 6.1 times 10 to the negative fifth times 6.1 times 10 to the negative fifth. I multiply those together. I get 3.7 times 10 to the negative 9. And make yourself a little note that there is no unit for Ksp. You don't write a unit on it at all. Straightforward? Yeah? All right, I want to do another example with you where we've got more than one ion where we have a coefficient, just as a practice problem, okay? So let's take a look here at manganese 2 hydroxide. If I write manganese 2 hydroxide in ion form, what do I have?
Mn plus 2.
Mn plus 2 and
Plus 2 OH minus.
2 OH minus 1s. Okay. The solubility of this compound is 3.6 times 10 to the negative fifth molarity, which means at equilibrium in a saturated solution, this is the maximum amount of ion that I would have dissolved, right? So, or that's the maximum amount of this that would dissolve. So if I have one of these, this is 3.6 times 10 to the negative fifth. But what if I have two of these? 2 times that, right?
7.2 times 10 to the negative fifth.
So this hydroxide ion concentration is 7.2 times 10 to the negative fifth. Okay, now my Ksp is the manganese ion concentration times the hydroxide ion concentration raised to the second power because of that coefficient in front of the hydroxide. I substitute in my concentrations. This is 3.6 times 10 to the negative fifth times 7.2 times 10 to the negative fifth, and don't forget to square that.
Do you square the 7.2 before you multiply it?
Yeah, I would. So you're going to end up getting 1.9 times 10 to the negative 13. Double check me on that. Make sure you get that. Okay?
Yeah.
Yeah? Okay, now I just want to make you aware that on Canvas, I tell you specifically if you're calculating the concentrations of something, when to round and how many sig figs to round to. So for instance, here, if you were calculating the concentrations of your ions in solution, you see how these are rounded to 2 sig figs each. So you would round them to 2 sig figs each, and then you would bring those numbers over here, and then you would use them to calculate Ksp, and then your Ksp would be rounded to 2 sig figs. But I tell you that on Canvas, okay? Okay, let's go the opposite way. I'm going to teach you how to calculate the concentrations of your ions or the solubility of the ionic compound based upon the Ksp value. So if you take a look at the next page has some reference Ksp values here. You may want to earmark this page because you'll be using it to flip back and forth while you're doing practice problems and a couple of the homework problems, okay? So just to reiterate, the Ksp value is not a concentration. It doesn't have a unit. The Ksp value comes from multiplying the ion concentrations from the saturated solution raised to a power together. And depending upon how many ions you have, if you have a lot of ions in solution, then that's a high molarity, then you would expect your Ksp to have a high value, okay? And then if you increase the temperature, you'll probably have more ions dissolved, and therefore your Ksp would be higher as well. So let's go ahead and turn to the last set of practice problems here, where we're going to calculate the solubility from the reference Ksp. If you take a look at A, we have silver chloride. Okay. They want us to calculate the solubility in moles per liter. They will often specify what unit they want. Like here is moles per liter, here is grams per liter, here's molarity, here's grams per liter. These are just unit conversions. So I'm going to do A and B with you just so you have a reference. And if we were to write our Ksp expression, this would be the silver ion concentration times the chloride ion concentration, and you would omit the solid. And then we would look back at the table on the previous page. You will see that the Ksp for silver chloride is
1.8 times 10 to the negative 10.
1.8 times 10 to the negative 10. Now, how am I supposed to get the concentration of my ions in solution? Well, couldn't I use a variable? So couldn't I just say, well, this is X and this is X? I mean, they're both 1, right? I have 1 of each. So they will have the same concentration. So I can substitute these X's in here. What is X times X?
2X.
X squared. How do I solve for X? Take the square root. So you're going to end up with 1.3 times 10 to the negative 5th molarity for your solubility. That is moles per liter. I'm going to do one more practice problem and then we're done. If you're looking at iron 2 sulfide, which is FeS, you're going to have an iron 2 ion and a sulfide ion. The Ksp expression is Fe plus 2 times S minus 2. I look back at the table for the Ksp value for iron 2 sulfide. It's 6.0 times 10 to the negative 19th. I have 2 ions. I'm going to substitute an X for them for their concentration, because their concentrations are going to be the same, right? This is X squared. Take the square root of both sides, and you're going to end up getting X is 7.7 times 10 to the negative 10th molarity. Now I can't stop here because they asked me for grams per milliliter, and molarity is moles per liter. So I'm going to take 7.7 times 10 to the negative 10th moles per liter, which is the same as molarity over there, and I'm going to convert moles to grams and liters to milliliters. Okay, so this is just unit canceling. 1 mole of, this is iron 2 sulfide, because whatever this concentration is, that's the concentration of this ion and this ion and this, okay? So that's going to be grams. The molar mass of FeS is 87.92, so moles will cancel. And then I can convert liters to milliliters. This is a one-step metric conversion. Milli is 10 to the negative 3, liters will cancel. Okay. So that gives you grams per mil. You're going to end up with 6.8 times 10 to the negative 11 grams per milliliter. Doable? Okay. You've come so far. Okay. You have 2 homework problems.